In this experiment, we are using the VEGA-3, and Cruz has divided it into two pulses that follow each other. And the goal is to use the first pulse to try to clean out electrons. And so we test that by bringing the second pulse in. So we have two pulses that we delay the pulses with respect to each other. And then we have a device that can tell us how many electrons that we are making. And we then delay the pulse, and we see whether or not we're cleaning the pulse out. Ultimately, what we want to do is study the vacuum. And studying the vacuum, we have to actually create a vacuum. And the particles that we need to get rid of primarily are electrons. Okay, well, that's a longer story. Now, with petawatt lasers, and this is a petawatt laser, it's very difficult to measure the intensity in real time. And the procedures most people use today is they make the laser run at very low powers, and then they try to measure it, and they hope and pray when they turn up the power that the beam behaves the same way. But there's good evidence that that's not true. So we have been developing, and we started this experiment actually almost 4 years ago now, trying to develop a way that we can measure the intensity in the focus in real time at full power. And we have come across a technique that we developed where we put in a little bit of gas inside the chamber, and the laser will then ionize the gas. The electrons that get freed then get trapped in the laser, and they get accelerated. And we call this sort of vacuum acceleration. And those electrons then carry information about what the pulse was. It carries information about the peak intensity. It also carries information about whether the pulse is aberrated or whether it's a really nice pulse. And we can look at, we basically take pictures, and we take pictures with film that your dentists use or doctors use to look at your body. And that film then has the distribution of these electrons, and then when we analyze that, we can tell what the intensity is and whether the beam has a very nice shape. So we developed that here at this lab. The first experiments were done in this lab, and so we're now using that technique because we can measure these electrons. We're using that technique to see whether or not we can clear out the electrons. And if we're successful at clearing out the electrons, then we can then start to think about how to measure the vacuum, which is it's an old problem, almost 100 years old. And it was predicted at the beginning of quantum mechanics, but it has never been measured, and we're trying to measure it. Well, there are many more steps in the experiment. The next experiment is we are going to go to a laser facility that has higher power. So in June, we'll go to a laser facility that has about 3 times the power of this laser, and we'll repeat these experiments. In this particular experiment, we used a parabola to focus the laser, but it has a long focal length. So the characteristic of the focus is what's known as paraaxial, which basically means it looks like a plane wave. And so all of our analysis has been done that way. And the laser that we're going to look at later on this year, it will have a very tight focus. So it has a very short focal length. So the spot is very, very small. And so all of the approximations we've made before are no longer valid. And so we have to develop new ways in which to analyze these electrons. And so that's the next step. And then the step after that is we'll go to a laser that has even more intensity. And we want to see whether or not the technique that we have developed will scale properly. And so we'll do 2 different experiments at the same time. One where we will ionize again an atom, and we will look at the ionization stage of that atom. And we know from theory that we can only ionize the atom to a certain ionization stage if the intensity is high enough. And so we'll compare that measurement to looking at our electrons to make sure that they give us the same answer. If everything works, they will give us the same answer. Usually that doesn't happen, and we'll have to go back and figure out what's wrong. And so finally, after that, we'll start to think about the real experiment by looking at the vacuum. The real experiment. It's a long-term experiment, so it'll be probably 5 years or more before we actually can do that experiment.